So this is a video SOP or standard operating procedure for the Instron 8874 machine. You can see the Epsilon biaxial extensometer here connected to the two cards on channel 3, and you can see here one of them is axial and one of them is rotational. So you're going to want to make sure that those are connected and that the correct calibrations are selected for each of the two channels here and here. So I will just set this here so we can discuss how to go through the sample preparation, setup, and running of a biaxial test. So you can see tubular sample here is typically what we would use to do a biaxial test. We have applied some coating here, some M-coat air drying coating here to the surface, and we've allowed that to dry, and the reasoning for that is to allow the pins that are in the biaxial extensometer to actually bite in to the surface. So you can see the biaxial extensometer right here, and it's going to actually clamp onto that area there. So you want to make sure roughly that you get the coating applied to the correct area on the sample that lines up with the 4 pins that are on the extensometer. You want to be very gentle with the extensometer, obviously. It's a delicate device, and you want to make sure that we don't do anything to damage the extensometer. We have all the safety and limits in place so that in the event that the sample does fail, the grips here are not going to actually do anything to damage the sample, or anything rigid will come in contact with the sample. So you can see that the machine is roughly set up here to the correct height. You want to make sure that if it is needing of adjustment, you can use the torque wrench or an Allen socket to remove the top 4 bolts on the crosshead there, and you can loosen them, as well as this yellow collar. And what that will allow you to do is then use the adjustment here on the side of the machine to raise and lower the upper crosshead to accommodate whatever length of sample that you want. Once you put it back together, you want to make sure that you obviously tighten the collar that prevents it from sliding down, the yellow collar, and then you want to tighten with the torque wrench here. You want to tighten the crosshead to 30 foot-pounds of torque in a crisscross fashion. So in order to prevent the sample from buckling under high gripping loads, there's specific plugs that you can use to actually get inserted into the ends of the sample, and especially for shorter samples, that's useful so that you have enough crosshead distance here to either use digital image correlation to measure the surface, or the extensometer to measure the strains that you're wanting. So the machine here has both force and torque transducers here, and then all the actuation is done at the top. So there's an alignment fixture at the bottom, some spacer plates, the transducers for the forces and torques, the hydraulic grip here and here, and then the actuator once again at the top. There is an adjustment here, control panel, that allows you to adjust the hydraulic grips, open and close them, and also jog the machine up and down. I can show you that happening here and here. To adjust the pressure on the hydraulic grips to suit your specimen, there is an adjustment knob here on the right hand side that allows you to change the pressure to suit whatever clamp load you need. So we'll go ahead and clamp the specimen into the grips, and you shall roughly line it up with where you want, and then click clamp on the lower clamp. And then now you can see obviously there's a gap between the upper grip and the top of the sample, so we're going to want to move this down. If the sample's not perfectly concentric in its dimension and it's bent a little bit, you want to make sure that you're doing this slowly so that you're not crashing the grip into the edge of the sample. And you're going to want to adjust this to the point where it's gripping sufficiently so that you have enough space here to use the extensometer, but also there so you have sufficient friction on the surface. So we will click grip on that, and I will now, before we click grip, I will go to the Instron software, the waveform software, so that we can, or wave matrix software that we can use to visualize actually what's happening in the samples. So you can see now this data that's being shown on the right here is live data. So if I press on the load cell, I press down, you can see more negative number showing here. So what we want to do is just clamp the sample at the top, and you'll see some preload being developed. And the objective now is to just have the sample under no load. So in terms of the axial and the rotational torque. So we can just open the software wave matrix and create a new project here. You want to make sure that you save it in a location that's meaningful with a meaningful name. And I will go to test users, and then we will say Andrew, and we'll say by Axial, and we'll say PR17, there we go. And we'll call it this file name here. And now it's going to prompt us, okay, well, what method? The test method is basically defining all of the specifications to how you want to run the test, which one you want to use. So we'll open one up here that we've created in the past, and we'll talk through exactly how it works to modify it. But this one is a load control biaxial in-phase measurement, so we can do that. So I will click next. Okay, so now we want to actually, before we do anything, setting all of our parameters for the test, our data logging that we want for the parameters we want to record, applying the extensometer. Before we apply the extensometer or affix the extensometer to the sample, we want to make sure that, first of all, the sample's under no dead load just from the clamping procedure. And we can see we have about 100 newtons here in compression, and the torque is about 0.2 newton meters in the negative direction. So what we can do here is use the set point tool, and we can say we want to select load and make the load 0, and we want to select torque and make the torque 0, and we want that to occur over a course of 5 seconds. This Instron wave matrix software is quite unintuitive compared to Windows, in the sense that you have to click enter to log one of these changes in any of these fields that you're selecting. So I'll click start, and you'll see both of these values start to decay to 0 over the course of 5 seconds. And then now we know that the sample's under no real residual load, which is nice, because then we can apply the extensometer and we can balance all of the directions of that extensometer to read 0 effectively, because we know that the sample's under no load based on the load and torque coming from the transducer. So now we can take our extensometer. There is a tool that we can use here to actually insert the extensometer a little bit easier. However, for the purposes of the video, I'm not going to use it, just for visualization purposes. The wires coming from the extensometer, we want to make sure that they're kind of out of the way and they're not going to get caught in the machine as it's moving. So we want to take the extensometer and we want to open it up. You can see that there's 4 pins here that are holding the extensometer rigid. So I want to still be gentle with it, but I can open it up, as you can see here, and I can apply it to the specimen so that those pins are digging into that M coating, that white coating that's there. And typically we can use a laser to define the location of this, but we want it to be symmetric and concentric on the gauge, and we want this to actually be measuring at the maximum diameter of that surface. So you can see that we can actually pick it up and move it around if we need to adjust anything, but we want it to be biting into the surface. And then you can see, because this sample is being controlled under load and torque control right now, once we pull these pins out, we will release the extensometer to move freely, and effectively this will allow it to follow the movements of whatever the sample is doing, because those pins are now biting into the surface. To make it a little bit easier to remove these, I like to twist the pins to stop any excessive bending or load being applied. It slides a lot easier when you twist them. So you just want to twist and pull depending on the preload on the specimen and the way that the specimen was machined. You might have more or less of this. So once you remove all of those, now you'll see the shear strain here on the top right and the strain, the axial strain here, are now going to be more noisy, obviously, because it's no longer locked. And these values are non-zero. So we can zero those out by going to the axial channel on the left here first. And we can go strain, and we want to balance. So strain, calibration, balance, and you can see that value went to zero now. It time averages over a little bit of time, so it might take a second for it to zero itself out, but you can see that there. And then you can see now on the shear direction, we're going to go to shear strain, same thing, calibration and balance. So now we have our extensometer set. What we now want to do is ensure that before we do anything to actually use the machine and move the actuator around, we want to make sure that the extensometer is protected and it's not going to get damaged. So we can see our position, which is probably the most important thing on the top left here. We want to make sure that we can go back to the axial channel and we can go to position. We want to make sure that our primary limits, which are safety limits effectively, we're going to set this to 48, which allows some movement as an upper limit, and maybe 44 for a lower limit. This is really dependent on the strain of your test. And you want to make sure you click enter there. That is a very common mistake. Make sure you click enter to save those parameters for your limits. And to enable the limit, you're just going to select this checkbox here. And you'll see when that happens, as you select and deselect, you actually enable each of these lights to occur here. So you can have up to four limits in the upper and lower threshold region for the axial and the rotational directions. So we have a limit set up for position. We have one set up for load here. Let's say we're going to go maybe to 1.5 kilonewtons, negative 1.5, enter. And similarly, we can do the same thing for the rotation, the torque. So for torque, let's say we want 2 Newton meters and negative 2 Newton meters. For this particular material, that's what we know from previous specimens, what we would expect. But in general, a hand calculation will support you to figure out what these limits should be for the very first test based on things like the yield strength and maybe a percentage of that with some safety factor. So now you're ready to start diving into setting up the parameters for the test itself and the method of the test. So we have our safety set up. You can also implement the rotational safety if you'd like. I won't turn that on right now, but you can turn it on similar to the other safeties or limits just by clicking these checkboxes. So now if we go to the method tab, you can see that there's 3 steps here that this test is going to run. First, it's going to balance all of the 2 directions of the machine. So it's going to balance the strain direction and the shear strain reading. Then there's going to be a hold in between. These are 2 things that are pretty much going to apply to all different procedures. The things that you really change here are the waveforms that you're going to be subjecting the sample to. So the first waveform at the top right here is your axial waveform. So we're applying the control mode of load. We're not going to do a strain control test here. We're going to do a load control test and measure the strain just for purposes of trying to do it as quickly as possible so you can see the hysteresis loops develop. So we want to do a load control test here, and we are going to do an amplitude of 500 newtons, and we are going to do a frequency here of, let's say, 0.1. So that's going to be 10 seconds to complete a full cycle. We can click enter. Sinusoidal waveform, we want to do 1e to the 1 million cycles, and we want no phase offset between the 2 different axes that you're controlling here. So we have 0 degrees of the waveform offset between the axial and torsional directions. If you want to do a non-proportional test with phase offset, you can just input 45 or 90 here for the phase angle delta. It doesn't matter if you do it on the first waveform or the second. Generally, it's the rotational direction that you're going to do it on, but just make sure you don't do both, because the effects of those will be combined. So we'll leave that at 0 because we'll just do a in-phase biaxial test here. And now we can go to the second waveform, which is torque, and we want to go between 0.2 plus or minus Newton meters, and we're going to make sure that you have the same frequency here. It's very rare that you want to have different frequencies, because obviously you're going to have kind of variable amplitude loading. Then it's not going to be a cyclic thing, and things will be out of phase all the time. So we want to make sure that we go to 0.1 here, sinusoidal again, 0 degree of offset. And the final thing that you want to do before you actually run the test is make sure that you're recording all the parameters correctly that you need. So we can go here to data processor, and all of these tabs allow you to change the amount of data that's recorded, the frequency it's recorded, and the type of data, the specific channels that you want to record. So in a cyclic test, often you want to do things like reduce the amount of cycles. You don't want to record everything. So sometimes we can do a reduction here of the data and not record all of it. Save tracking, we can skip every 10 cycles, 100 cycles, 1,000 cycles. We can do logarithmic acquisition. It's really up to you, but being consistent with whatever your specific requirements are for that fatigue test is important. You can save the peak and valley, so you can use the peak and valley detector in the wave matrix software to save the peak and valley, so you don't have to extract it after the fact from the cyclic data. That allows you to look at trends a lot easier. And we could also plot things while the test is running. So we want to monitor specific things, plot specific things. This is all set up in this particular method, but obviously you can adjust that to suit your needs however you want. So now that that is pretty much taken care of, we can go to end actions, and when we end the test, we want to know, well, we want it to always transfer to either a specimen protect mode, but if the specimen fails or we end the test, we want to make sure that we can actually stop the sample from moving excessively. So we want to probably put it into a displacement control mode. That's kind of mandatory to ensure stability if the specimen is no longer connected, or there's a crack, or there's a large displacement. So you definitely want to have it default into displacement control mode to lock the machine in position, and that way you can extract the sample easily and safely. You never want to put your hands close to a machine that's running in strain or displacement or force control mode. So yeah, that is pretty much all we would want to test here. And we can see that the position and the rotation of the default modes that it's going to get dumped into or default into after the test is completed. So we'll go back to resource or sequence here, and we will click Save As on this method, and we will say cyclic biaxial in-phase load control. You want to make sure you save it. If you make changes, it won't let you validate until you save it. So we'll say Save. I'm going to say, do you want to replace it? We can choose to or not. Yes. So now we can go back to the test tab, and we will click Validate here, and it's going to check our test to make sure we have the right resource allocation in terms of the right cards plugged into the right sensors, assigned to the right resources in the Wave Matrix software, and it's going to check that we have a cohesive and completed method that allows something to run from start to finish. And we see where there's no errors here. If there's errors, it generally will give you a somewhat cryptic phrase that will allow you to basically log or dive into how to fix it. And then what we want to do, we can click Start here, and the test will initialize. We want to make sure, once again, obviously, that we're watching the test and making sure that we're ready to adjust any limits if something gets tripped. So we can click OK to start running the test. and you'll see now the forces and the torques are changing. Since the test frequency is so slow and the amplitudes are quite low, you won't see a lot of updates on the screen. You're going to see an update every 10 seconds. So you should be able to see on the left, you'll see a axial stress strain hysteresis loop, and on the right you'll see a shear stress strain hysteresis loop. So the shear actually is getting influenced by the fact that I used a failed sample here with a small crack in this video SOP to demonstrate the type of data that you might get obviously in a situation where that's occurring. So we have some area here. I can do this without a lot of force now. We can show some area in the hysteresis of the shear strain, and the axial strain pretty much looks as you would expect for a low amplitude test. The other things that are showing the live data is all on the top of the screen here. All of the max mins and the setup test parameters are on the bottom. So we've accumulated 7 cycles here. You can see our axial forces were perfect really from the first cycle here on the left. That's hitting the peak and valley targets quite easily. We can rescale this by clicking auto scale, right clicking and then clicking auto scale. It took 2 or 3 cycles for the shear targets to get met, and now you can see that the test is running happily. Basically now we monitor the test to ensure our limits are set up correctly. So we want to use the information for the peak and valley here to make sure that the limits are set correctly, and we want to make sure that if we're going to leave the test unattended, that all of those are set to a point where it's safe to walk away from the test. And once the test is completed, if we've set our end actions correctly and our specimen protect correctly, we should come back to a failed sample or something that's reached an infinite life, and then we can post-process the data according to that type of information that we're getting in the CSV file that will be provided by the Wave Matrix software or exported from there. And with that, I will sign off from this video SOP to, I'll pause the test before we leave just to show you if in the case that you do need to pause it, what can you do. So if you click pause here, the test will stop exactly where it is, and you can see that it's going to default to the control modes that you've set up in the Wave Matrix software in the pause event. So this allows you, in case you need to adjust something or check something or go close to the machine, this will allow you to pause the test. If you want to remove the sample and say you have to give the machine to somebody else, or you have to shut down the machine due to a power outage or a vacation break or something like that, you want to make sure that you're not leaving the test unattended, where it can potentially go unstable if there's a hydraulic system update or a power outage or something like that. So that is something you want to make sure that you're diligent of. But other than that, yeah, this is a complete summary of how to run a biaxial test in force control mode and torque control mode, but monitoring the strain using the biaxial extensometer. If you have any questions, obviously reach out to the lab director or any of your superiors they might be working with. If you have questions regarding what type of data you should be collecting, if this is your first type of test, it makes sense to do something like this with a mentor or someone that's working on the project with you to kind of supervise a little bit. But yeah, thank you, and enjoy testing.